Alright, this is gonna be quite a long video. I'm already exhausted because I just came out of 4 hours of straight teaching students topics ranging from pre-algebra all the way to Calc 2. So I apologize if I sound a little exhausted, but I'm still going. I'm still trying to keep up here for this specific video because I'm just so much in the math mood right now. So really, by the end of this video, you are going to fully understand the analytic techniques of differential calculus with respect to polynomials and really just all the stuff without trigonometry. Okay, for now. Maybe if I feel like it, we may get into the trig derivatives, but for now, it's really just going to be mostly polynomials, and actually, I'm going to do this in a very weird way, and you're going to see that I'm going to teach this stuff in a sequence that's kind of atypical to how a Calc 1 teacher will teach these concepts, but I believe it's for the better. And so I'm not going to spoil anything, just some kind of prerequisites. Of course, you need to know algebra. Trigonometry, you don't technically for this video, but you should know trigonometry if you've done pre-calculus and algebra 2 and stuff like that. And also limits. I'm going to assume you know what limits are and how limits work and at least the notation behind limits, but it should be kind of intuitive even if you don't know what limits are, especially with the approaching. So if you don't fully know limits, but you're aware of the notation, because I am going to use limit notation, especially like right when we start now with the classic problem, I'd expect that you know limit notation, but at least you, even if you're not fully aware of limits, you should still be able to kind of understand what's going on. But I kind of expect these prerequisites when you if someone asked me what do I need to know to understand this video, that's what that's what I just said. So know your algebra. Algebra is going to be a huge component in this. Logs and exponentials as well. It's going to be a packed video. So let's get started here with the classic problem. So I'm going to draw a coordinate plane right here, or let's just say quadrant 1 of our Cartesian plane. And I'm going to just draw some kind of function here with 2 points. I'm going to draw some kind of curve. I don't know. Maybe it looks like this and kind of goes on forever. And what I'm going to do now is I'm going to kind of sketch a secant line. Now, a secant line, for those who are not familiar, hopefully you've taken, maybe I should mention this, some geometry as well. A secant line, you probably heard of that relative to a circle, but in this case, just it's a slope, it's a line formed by 2 points. It's just a line. You have 2 points. 2 points give you a line. Okay, so it's a secant line is essentially that. So this is the secant line formed by these 2 points, okay? And so now I want to find the equation of this secant line. Sorry, I keep grabbing my water. My mouth is a bit dry here, but anyway, we have this secant line here, and I want to find the equation of this line. So again, I told you 2 points form a line, and of course, I want the slope of this line. We have to do, let's go back to algebra 1, y2 minus y1 over x2 minus x1, rise over 1. I want to find the slope of this line. Okay, so in order to find the slope of this line, we need a y2, a y1, and an x2, and an x1. So I'm first, without even going to that, I'm going to just get 2 points. So I'm going to call this x, okay, call this x, and if we plug in x into a function, let's call it f of x, this is going to be, our output here will be f of x, okay, f of x is our output, but then here, I'm going to call this input here, or this x value, x, and then plus, I want to get it, I want to get this, forget I wrote this for a second, I want to get this input, or this x value, in terms of this input, which is x. So I'm going to call it x plus some distance to get from here to here, because if I want to get it in terms of this, we already have this x value, right? But I just need to find a distance add a distance to get to here. And so, because there are going to be some changes involved, as you're going to see, I'm going to call this, and again, this may not make sense for like why I'm calling it this now. I'm going to call this the change in x. Okay, and we sometimes call this delta x. It's a Greek symbol, delta. It's typically associated with change. If you've taken like some science classes, like chemistry and physics, you've probably seen this. If not, that's fine, but this is typically associated with change. You're probably like, Vade, where is the change in this? Well, we're about to see what the change is. So just be patient. I'm going to call it this for now. Some people also call it H as well, but I'm going to call it this because there are going to be some changes, and we're going to see that in just a second. So we input x plus delta x, and this should make sense, right? I want to get this input in terms of this input, so it's this input plus a distance, which I'm going to call delta x, because eventually this distance will change. So I'm just going to draw kind of like a line here to show that the distance from x and x plus delta x is delta x, or the change in x. And you're going to, hopefully this makes sense, because if you do x plus delta x minus x, you just get delta x. Okay? And so now if we plug in x plus delta x into our function, hopefully we realize because this is f of x, this should just be f of x then plus delta x, right? Because inputting x plus delta x, output is f of x plus delta x. So now we have our 2 points. Yippee! So now it's just we have x comma f of x, right? And then we also have x plus delta x comma f of x plus delta x. Isn't that beautiful? Okay, and so we have this, and so now we can use, again, I was talking about this earlier, and you should know this from Algebra 1, the slope between 2 points can be found by doing y2 minus y1 over x2 minus x1, or rise over run. And so I'm going to call this x1, y1, I'm going to call this x2, y2, right? Okay, and so now if I want to find our slope, or m, and I'm going to call it, just because it's more appropriate here, we're going to have a different slope at the end, and that's going to kind of introduce us to the world of calculus, differential calculus. I'm going to call it the m secant, right? Because, again, I talked about this, it's a secant line, and hopefully you understand it's just, again, just line formed by 2 points. So this naming should make sense. So this is going to be y2, which is f of x plus delta x, then minus y1, which is f of x, all over, and then x2, which is x plus delta x, minus x1, which is x, and then these will cancel. These x's will cancel, so we're just going to get m secant equals f of x plus delta x minus f of x all over delta x. And maybe this looks familiar. Some people, or you may have heard of this as the difference quotient. If you've not heard of this at all, or not seen this at all, or your teacher has not asked you in pre-calc or algebra 2 class, hey, evaluate this, or maybe you've seen this as an h, f of x plus h, I was talking about this earlier, minus f of x over h. Maybe you've seen this expression before, but you didn't know what it is, but now you know what it is. Anyway, yeah, this is what we call the difference quotient, which is essentially just the slope of this secant line. So, you're like, Vade, why is this so important? Where's the calculus here? You were just doing Algebra 1. Any Algebra 1 student could do this. Well, wait, okay? Now let's get to the delta x. Why I even called it delta x, the change in x. What are we about to change here? Well, imagine this distance, right? We're going to change it. We want it to get smaller and smaller and smaller. Okay, this distance is going to get smaller and smaller and smaller. Okay? If this distance is getting smaller and smaller and smaller, it's eventually going to be 0. Okay? And so now you realize that if this distance is going to get smaller and smaller and smaller, again, it's not necessarily going to equal 0, but it's going to infinitely approach 0. We can say that this will be delta x approaches 0, right? And so as this delta x approaches 0, this line, right, this line is turning into this line. Okay, this line is actually turning into this line, right? You can kind of see the transformation, right? As we're getting closer and closer, closer and closer, right? We're eventually going to get this line right here. And what is this line called? It's called the tangent line. And you've probably heard of this tangent line again if you've taken geometry. Relative to circles, perpendicular to its radius. But this tangent line, again, it's the slope at a point. I was talking about how, or it's also like it's a line at a point. And I was talking about how a line has to be formed by 2 points, right? In order to find the equation of it. But here we actually have a line formed by 1 point, and that's called the tangent line. So it's and this here, right, as delta x approaches 0 of the slope expression, this will give us the slope of the tangent line. So this secant line, it's slowly and slowly and slowly becoming the tangent line as this distance gets smaller and smaller and smaller and approaches 0. So again, this is where limit notation comes in, right? Delta x approaches 0, right? I'm saying delta x approaches 0, better or formal way of calling this, but again, you can just think of it as delta x getting smaller and smaller and smaller. The limit as delta x approaches 0 of this slope expression right here, f of x plus delta x minus f of x all over delta x, right? This will then equal to the slope of the tangent line. And then this leads us to the start of differential calculus, where we're all about finding the slope of the tangent line at a particular point of a function. The slope at a point of a function. So that's kind of weird, right? You think that, oh, I need to find, the only way for me to find the slope of a line is if I have 2 points. Well, that's not necessarily true now. And maybe now, as you see here with all these different lines here, like why a tangent line may be useful. Well, think about what happens when the slope equals 0. Let's say we have some parabola here. And let's say we have we have a tangent line right here. We have a tangent line right here. And wait, what about a tangent line right here? It's horizontal. It's a horizontal line. Slope is 0, right? Horizontal line has a slope of 0. And what else do you notice at this point where there's a horizontal tangent? Hey, there's a maximum here. There's extrema here. Now you're probably, Vade. You're giving me a quadratic. I can do this without this whole tangent line thing. If I just do opposite of b over 2a, find the vertex. But wait, what if we had something like this, which is not a quadratic? Now how will I find these? I can't do opposite of b over 2a since this is not a quadratic. But wait, I can find the tangent lines, these horizontal tangents, and there we go. So now, I'm not wasting your time, right? You can't do opposite of b over 2a for something that's not a quadratic, right? In this case, this looks more like a quartic, right? How do you find the extrema? How do you find the maximums and minimums? You gotta find where the tangent line, the slope at a particular point of this function, has a horizontal tangent. And so this may not make sense right now because we've not done any problems regarding this, but as you will see, this is one of the main reasons why we learn this stuff. Because in instances where we can't just rely on the properties of a parabola and other stuff, you gotta turn to this stuff. So again, may not make sense right now, but trust me, there's usefulness to this. All right, so this is our limit definition of the derivative, okay? And so what is a derivative? Derivative is just instantaneous, at a point, at an instant, the slope of the tangent line of a particular function. That is the derivative. That is what the derivative means. Okay, and we're going to talk more about notation kind of as we go, but for now, think of it as m tan as something known as, if we have f of x, the derivative of f of x, and this is called Lagrange's notation, this is going to be called f and then a prime here of x. Okay, maybe you've seen this prime symbol before in geometry or trigonometry, but here we are. Okay, f prime of x, the derivative, the slope of the tangent line, the instantaneous rate of change, that's equal limit as delta x. This delta x is getting smaller, smaller, smaller of the slope of the secant line. This will give us the slope of the tangent line at x. Beautiful stuff. Excellent stuff. And hopefully this makes sense. Okay, and now we're going to move on to just a practice problem to kind of help us grasp this stuff. Before we get into the next concept, I want to just do a practice problem here to kind of get us used to this concept. Hopefully you find this quite interesting, and if you have questions, maybe just keep watching and you will eventually get it. But if you're really stuck and you've watched until the end, just don't hesitate and ask any questions you have in the comments section, and I would be more than happy to answer them for you. Okay? Sorry, it's taking a while to erase this. Make sure it's spick and span. Now, let's do a practice problem here. So let's say that we have let's say f of x equals to x squared. Okay, this is a classic one. I want to find an expression, an equation that can help me find the slope of the tangent line of this function at any single point. So in other words, I need to find f prime of x. So remember, f prime of x, and we just derived this, is the limit as delta x, or some people call it h as well, but we're going to use delta x because that's more intuitive. We just learned why, because that distance is changing. Delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And don't overthink this. This is like, how am I going to use this to get to this? It's just function notation, right? What is f of x plus delta x? F of x plus delta x. We plug in del x plus delta x in for x. So this is going to just be x plus delta x squared. Okay, and then what is f of x, right? F of x is just x squared, right? And then delta x is just delta x. So let's just continue this here, right? Limit as delta x approaches 0. F of x plus delta x is x plus delta x squared. F of x is x squared. And then all over delta x, which is just delta x. Don't overthink it. So now, we want to FOIL this out. We want to expand this. So this will just be limit as delta x approaches 0. And you can, if you want, write it as just x plus delta x times x plus delta x. And go from there, do the foiling. You can do this if you want, but I just know here I'm going to use a squared plus 2ab plus b squared. You can even use Pascal's triangle or some binomial expansion if you're really feeling fancy. Just x squared plus 2x delta x plus delta x squared, and then minus x squared all over delta x. And so now we see that this x squared cancels. Okay, good. We're seeing some canceling. That means we're doing something right. And then, well, I mean, in this case, sometimes canceling is not a good thing, but in this case, it feels good, right? So limit as delta x approaches 0 of 2x delta x plus delta x squared all over delta x. So where do we go here now? Again, if you're familiar with limits, right, we always try to directly substitute, right? Again, I'm sorry if I kind of skipped this step, again, especially if you're not that comfortable with limits. You try to first directly substitute the 0 into this expression, but if you see this, we'll get f of x plus 0, which is f of x, minus f of x, which is 0, and then over, then you plug in 0 in for here, you'll get 0 over 0, and 0 over 0 is indeterminate. We don't know what that equals. So then we have to either use something, for now I'm going to say this, the only way to solve this case is to use some analytical techniques like this. Like first we expand it out, see if things cancel, and by things canceling here, especially this denominator, then we'll be able to evaluate this limit. And if not, we have to switch to either a different technique or the limit does not exist. So for now, the only way to do this in an indeterminate case is through, of course, analytic techniques like this. And of course, later on, I'm not going to cover it in this video per se, but there's a rule called L'Hopital's rule, which essentially, if you have any limit in the indeterminate form, you are able to do it, evaluate that limit using that rule. But we are not going to go over that in this video. Okay, so now, like I said, it's really good if we can have the denominator cancel, because we still plug in 0 into here, we'll still get divide by 0. That's not good. But hopefully you see here that we're now have delta x factors in each term in the numerator. So we can just rewrite this as the limit, as delta x approaches 0, of 2x delta x over delta x plus delta x squared over delta x. And so here we hopefully see this cancels, and then this cancels, and then this is a 1, so we get the limit as delta x approaches 0 of 2x plus delta x. And now hopefully you see here that if we plug in 0 in for delta x, this is just going to be 2x. So therefore, this is a fancy symbol for using therefore in math, for saying therefore in math, f prime of x equals 2x. And so again, what does this mean? Did I waste my time doing this? No, because this is a function, essentially, that lets us find the slope of the tangent line at any x value, any point on x squared. So for example, if I sketch y equals x squared here, a rough sketch, okay, and I want to find the slope of the tangent line at, let's say, x equals 3. Okay, I want to find the slope of this tangent line right here. Okay, and so if I want to do that, I just have to do if f prime of x, which is our, let's say, I'm going to rename, since we may not be comfortable with the notation right now, I'm going to call this m tan generator, I don't know, like function. M tan function, and then that equals to 2x. So we just do m tan function of 3. That's just going to equal to 2 times 3, which is 6. So the slope of this tangent line right here is 6. Okay, now what if I want to actually find the equation of this line? Okay, now I'm kind of pushing this a little bit, because I said initially, right, you know that you need to have 2 points to form a line, or to find the equation of a line perhaps. But what if I tell you right now that just by looking at this line, which is based off of this one instant, this one point, this one x value right here, since we're dealing with functions, how can I find the equation of this line based that is established because of this instant or this x value? And that's really easy, because if we have a slope and then we have a point, we can then also have a line, right? Point slope form, right? And so what I mean by this is, if we have the slope, a point, right? We know that this is at x equals 3. So what is this actual point right here on x squared? Well, if we do f of 3, f of 3 is just 3 squared, which equals 9. So then we know that this point right here is 3 comma 9. Sorry if this is not drawn to scale here. So this point right here is 3 comma 9. So point and slope. So the equation of this tangent line right here, which is based off of this one point, is just, again, point slope form, which is y minus y1 equals m times x minus x1. Right? Again, algebra 1 concept. Hopefully you know that. You can also slope intercept form as well, but y minus then y1, which is 9, equals to 6 times x minus 3. That is the equation of this line. right? And so we can write it in slope-intercept form, 6 times x minus 3 plus 9. Do distributive property, it's going to be 6x minus 18 plus 9. And then this is going to be 6x minus 9. So the equation of this tangent line right here is y equals 6x minus 9. Isn't that really cool? And so now what I told you here, again, I use a parabola because, again, if we want to do x cubed and stuff, x to the fourth, we can do that, but it's just more work. I'm just showing this to you for example's sake. If we want to actually, again, I told you one of the applications behind this is to see, hey, when the tangent line, when the slope is 0, we can find where there's extrema. So in this case, we know that the slope has to be 0 here, and that's where the vertex is, or where the minimum is. And we can actually see that here because we have the m-tan function 2x. So if we set this 2x equal to 0, we know that x equals 0, right? So then where x equals 0, that is the location where there is a minimum or a maximum, a relative minimum or a relative maximum. So that's really cool. And we'll talk about, there are some, like again, what I mean by this is, of course, when we're dealing with polynomial functions, where they're continuous everywhere, sometimes we'll be given closed intervals, and so a maximum or minimum could actually be at an endpoint. So now I'm generally just saying, right, you see these curves, right? Like if we have a cubic here, let's bring in a cubic now, right? If we have a cubic here, or no, let's not do a cubic. Let's do another quartic. I don't know. Right? If we do something like this here, again, like if we know that because of the shape of the curve, right, this has a local max, local min, local max, stuff like that. But sometimes you can be given endpoints, right? Like let's cut this off completely, essentially. And you could be given something like this, essentially, and I can even make this better, like this. And because we're cutting off that domain of all real numbers, you'd think that this is the smallest y value of the function, but technically it isn't because of this closed domain, so it's actually here where it's the minimum. But this is still considered a relative minimum, okay? And I'm sorry for derailing here, and if you find this confusing, that's totally fine. I don't expect you to fully understand what I'm talking about here, and it's not necessarily important for this video per se, but it's still like, I just want you to not blame me in the future when you say, hey, this doesn't always show me the minimum or the maximum, because it won't. You have to compare the values that you have. And so part of that comparison is, again, where this horizontal tangent lines are. Okay, so that's a quick intro here. Limit definition, how we use it, how we can get these m-tan functions, these m-tan generators. Okay, so now we're gonna dive into the analytic techniques, okay? And so now, again, this is one of the analytic techniques. Again, this video per se is not necessarily again, I showed you an application of this. We'll talk about more of the applications in a later video. I'm just showing you why these help. Why these help. But again, now we're just going to go on to how we can actually just do more of these, like how we can find more of these generator functions, these m-tan functions. Okay, that's really, again, no one really calls it that. That's just my own nickname for it because that's what makes sense. This is the function that gives you, that gives you the slope of the tangent line at any point on a function. And on this function in particular, because we found it because, you know, we did it based off of x squared. Okay, so now we're just getting the analytic techniques, how we can find these functions for more complicated functions, and now we're just going to go step by step regarding this. So this is our brief intro, and so now I'm just going to erase the board here. I highly recommend you remember this, okay, limit definition. You can also derive it if you're really stuck. Again, you can derive it in 5 seconds. It's like, hey, let me first create a secant line, and then, hey, let's have that delta x get smaller and smaller and smaller, and then hey, we have limit definition, okay? That's really all this is, okay? And now I showed you a bit of the significance, but now we're really just going to head into how we can find these mtan functions, these derivatives, f prime of x's, that can actually be found for like more complicated functions, right? Like what if we have something like f of x equals to the square root of e to the x plus 5. Okay, that's like, again, that we can't, limit definition here won't really help us that much. Or it may, but it would take 10 years to do this. Okay, so that's where we have these analytic techniques, and then oftentimes now teachers will go ahead and just give it to you and expect you to memorize them. But no, we're actually going to go through this step by step in a sequence that's really, really weird, but very concrete for students to actually understand these analytic techniques, okay? So now we're going to go into something called the chain rule. And so what the chain rule is essentially, say you're given, again, like I just gave you here, let me pick another example, like, let's say let's stop with the square root. It's like, let's say we have some function like x minus 3 to the 5th, right? F of x equals x minus 3 to the 5th. What do you notice about this function? Well, hopefully you should notice that this is a composition of functions. And so how we can essentially abuse the fact that this is a composition of functions, we can easily find the derivative, or this mtan function, or again, f prime of x. Essentially abusing, I know that's a very bad term to use, but again, like essentially taking advantage of, is I'd say a better word to use, of this fact that it's a composition of functions. So let's essentially say, define a composition of functions as f of g of x. Okay, and for example, this should make sense. Like if we want to identify f of x and g of x, like the outside function, the inner function, right? F of x is the outside function and g of x is the inside function. We can say that f of x is x to the 5th, and then g of x is x minus 3. So then f of g of x is just, sorry if the light is kind of blocking it, f of g of x is just going to be f of x minus 5, which is g of x, right? And then that's going to be f of x minus 5 is just x minus 3. This is x minus 3, and so then plug in x minus 3 in here, and this is x minus 3 to the 5th, and that's exactly what we had here. Okay, so hopefully this makes sense. So now, let's actually get into how we can utilize this f of g of x in order to find derivatives of composition of functions, these mtan functions, which are really useful for us. And we'll talk about applications in another video, but this is more or less how we can find better analytic techniques and understand why I'm able to get to these. Okay. Alright, so now we're going to get into something called the chain rule, and again, I was mentioning this a lot. Again, we're going to take advantage of the fact that we have or have identified a composition of functions. And now at first it may be a little bit like, oh, f of x is what again, g of x is what again, but the more and more you do this, the more it becomes kind of muscle memory. Like, oh, I know that this resembles like x squared, like really, you know, like what the outside function is. Like if you see, again, we were talking about like something like x plus 5 to the 9th or something like that. Hopefully you realize that, hey, yeah, this looks like the outer function, like this resembles like an x to the 9th kind of thing. So that's really what we're trying to look for. And we'll, again, right now it may be a little difficult, even though, again, you should have learned this in like algebra 2. This will eventually become kind of muscle memory. So again, let us recall, remember, f prime of x, the tangent function, okay, the slope of the tangent function, generator, whatever you want to call it, that can help us find the slope of the tangent line at any point on a curve. Okay, that is, you can find that through the limit definition. Limit as delta x approaches 0 of f of x plus delta x minus f of x. all over delta x. Okay, so make sure you know that. Again, you can rewind or look it up if you don't remember it as of right now. I don't expect you to, unless you are really good at remembering things very fast. But right now, I'm going to write it in, I'm not going to explicitly say recall this, just you should know it. Okay, so if we want to find, let's say that we have, again, f of g of x, right? F of g of x. And we want to find this, again, sorry, camera's not surely. We have f of g of x, right? And we want to find that function, okay? We have to do limit definition, okay? So, I'm going to just say m. Right now, we don't fully know the notation. We will talk about you will kind of learn more and more about the notation as we go. Maybe if we have time at the end, I can talk more about it. It really depends on my mood, if I have the energy. I'm already running out of a lot of energy, but I want to get through the stuff that we need to get through. So anyway, we want to find the m tan. Let me try to use more of this space right here. The m tan function of f of g of x. We have to use limit definition here, okay? So it's a limit as delta x approaches 0. And this is where, again, don't let all these variables confuse you, okay? Remember, in f of x plus delta x, we plugged in x plus delta x into this x right here. It's just function notation, okay? You should know function notation. So please just get comfortable with the fact that this will just be, instead of f of x plus delta x, it's going to be f of g of x plus delta x. And then minus, okay, f of x, like we see in the typical one, f of g of x. And remember, delta x is just delta x. Okay. And so now I'm going to do something which is a little weird, but it is correct analytically, but it may seem a little ambiguous right now, okay? But it's a kind of manipulation technique, analytic technique perhaps. And so what I'm going to do here is I'm going to multiply the numerator and the denominator by g of x plus delta x minus g of x. And then here I'm going to also multiply, again, denominator by g of x plus delta x minus g of x. Okay, so numerator and denominator are being multiplied by g of x plus delta x minus g of x. Okay, g of x plus delta x minus g of x. Okay, it's a little ambiguous, but this is how the proof works. But again, this should make sense why I'm allowed to do this, because these just cancel and then you just get this. Okay, so it's really this. This is the same thing as this. Okay, so again, what I'm doing is correct though. Okay, in terms of the rules of algebra and mathematics. Okay, so now I am going to do a little bit of rearranging here. I'm going to move this guy with this guy, and then I'm going to move this guy with this guy, okay? I'm just going to, and again, this is also allowed. You can switch these denominators. We can do that because, again, this is 1 over delta x. This is 1 over this. You can switch them around. That's totally fine with multiplication of fractions. Okay, you should, again, this is all of what I'm doing is allowed. It may seem, the only question you may be having right now is why I'm doing this. And you're going to see as I show you how this kind of works out here. Okay, so now we'll get limit as delta x approaches 0 of f of g of x plus delta x minus f of g of x all over g of x plus delta x minus g of x. Okay, and then that times g of x plus delta x. And okay, I'm going to have to kind of skip a step here because we're running out of space. But essentially, I can write this limit twice. And what I mean by that is if you have a multiplication here, the limit of this entire thing is the same as the limit of this guy times, again, the limit of this guy. So the limit of this guy times the limit of this guy, again, same, delta x approaches 0, is the same as the limit of this entire thing as delta x approaches 0. So I'm going to rewrite this, again, with another limit, as, again, these have to be the same. That's the reason why I'm saying it works, as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. So I just did some rearrangement here. Again, pause the video so you can kind of analyze, but this should make sense. Okay, why this is the same as this, okay? And so now, hopefully you see here that this guy right here, this, you should know what this equals to, right? With respect to the little bit of derivative notation that we already covered, right? This, if we replace this with an f, right? F of x plus delta x minus f of x over delta x. In this case, it's just g of x plus delta x minus g of x over delta x. This is just g prime of x. I don't know if you can see that. This is just g prime of x. So we can rewrite this as just the limit as delta x approaches 0 of this same guy right here. We're going to talk about this guy in just a second. Just copying down all over g of x plus delta x minus g of x. And then here, this will be g prime of x. Okay? So hopefully that makes sense. So now, let us state some facts. Okay? So I'm going to let n, okay, just some other variable n, equal to g of x plus delta x minus g of x. Okay, and so again, if I want to say here, okay, what I'm about to say may be confusing, but I'm going to let you know. So why this works. So as delta x, change in x, approaches 0, n approaches 0. And why is this? So as let's pretend for a minute that we're going to do some, let's just not pretend, let's just directly substitute to see why this works. Let's say that delta x equals 0. Let's say that delta x is 0. Well, if delta x is 0 here, we plug in 0 into this guy, then we'll just get g of x minus g of x, and that's going to be 0. So if n is equal to g of x, if n is equal to g of x minus g of x, which is equal to 0, if delta x equals 0, then n will also equal 0. So therefore, as delta x approaches 0, which would mean that we'll eventually get g of x minus g of x, which is 0, which is then equal to n must also approach 0. Okay, and so now, if you think about this, if we move this to the other side of this equation, okay, and again, what I'm doing is a little ambiguous, but again, hopefully, this is a really important thing to understand, right? As delta x approaches 0, we'll get the g of x minus g of x equals 0, which is then n equals 0, so n must also approach 0. Okay, so now we have this fact. Now I'm just going to move this g of x to the other side, so now we get n plus g of x equals g of x plus delta x. Okay, and so now, if we just substitute g of x plus delta x in for n plus g of x, we'll get limit. And then I'm also going to write this as a limit of n, right, as n approaches 0, because as delta x approaches 0, n also approaches 0, so this will be n approaches 0 of f of then g of x plus delta x. We said that that is now n plus delta x, or n plus g of x, sorry, n plus g of x, okay, and then minus f of g of x, this stays the same, all over, then here, this is n, okay, because remember, let n equal to g of x plus delta x minus g of x, right, this is n, all over n. Now, what does this kind of represent here? I'm going to draw a thought bubble. Okay, you may not see it right now, but hopefully you realize it's just limit definition of different variables. I'm going to draw kind of like a thought bubble right here, okay? Okay, so let's first say, like, again, the reason why I'm drawing a thought bubble is because I don't want you to get confused with this delta x and the delta x I'm about to describe in this. Okay, so let's just say, again, completely separate problem. We just have limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, this is just some completely different. Ignore this, but except for this. Look at this, okay? Because I'm trying to connect this to that, okay, by just rearranging stuff, okay? So hopefully you realize here that, first of all, delta x is n, right? So this delta x is just n, okay? And then this x, instead of x, we're actually plugging in g of x. So this g of x becomes this x right here. Okay, completely separate problem, okay? Just this delta x is not the same as this delta x. This is completely separate. I'm just looking at this limit definition itself and seeing like how this resembles that. That's really what I'm doing. And so if I show that g of x equals x and then delta x equals n, I can then rewrite this as the limit as delta x approaches 0. Wait, that's just n approaches 0 of f of then x, which is g of x, or again, like g of x, and then plus delta x, which is n, and then minus f of x, which is then f of, then x is g of x, and then that all over delta x, which is n, which this is the exact same as this. So I showed how this resembles the limit definition of the derivative. Again, n, g of x plus n is the same as n plus g of x, as you see here. Again, just property of addition. That should make sense. So this, now what the purpose of this is just that, hey, this is just the limit definition of the derivative. Okay? That's all this is. So now what is this? What is this? So f prime of x, right? This is f prime of x. This equals f prime of x right here. Now what is x? X is g of x. So this is just f prime of g of x. Now I gotta write this g prime of x here. This g prime of x is still there, right? Just going from here to here. This is f prime of x, which is then f prime of g of x. Since this, instead of an x here, we have a g of x here. Instead of an x here, we have a g of x here. So this is just going to be, instead of f prime of x, it's going to be f prime of g of x. And then that times g prime of x. So that's the m-tan function of g of f of g of x. The derivative of this is this. Okay? The derivative of this is this. Okay? Isn't that awesome? That's really cool. That's great. So we're going to come back to this. We're going to use it. But now I just want to bring up something else. Okay? Now that we know the chain rule, make sure you know this. Again, I don't expect you to memorize it right away. Just look it up, because I'm going to refer to this rule. So yeah, it's just really composition of functions. Actually, let's do a practice problem before we move on to the next thing here. But again, derivative of this, that slope function, to find it for any x value, you just do this. Yeah, you just do this. Okay, so hopefully all the analytic work that I did makes sense, okay? Why I'm able to deduce these things. Again, some of the multiplication here was ambiguous, like why did I do it? Why did I do it? That's just how the proof works, but why it works, that's what you should understand. Like, I didn't violate any algebraic properties. I think that itself is the most important thing, to understand how I am able to rearrange stuff and stuff like that. But that idea itself of multiplying this and that is something that is, again, like a more abstract idea that again, the person who created this proof would have had to contemplate about for a while. Again, that's what I think. If you know of explicit reason why you would do that, then let me know in the comments. But again, for now, I would just say you're just doing it because it'll help you later, but it doesn't, you're not doing anything wrong. I'm running out of water. Okay, let's do an example problem before we move on. So let's go back to a kind of, I don't know if I use it like x plus 3 to the 5th or something like that. I don't remember. X plus 3 to the 5th, and I want to find the derivative of this, okay? I'm going to not use, we'll get to notation in just a sec, okay? So just bear with me, okay? Let's just call it for right now. I want to find the function that generates the tangent line, the slope of the tangent line, and essentially it essentially does also generate the tangent line, because once you have a slope, you can then find the point by just plugging in that x value where you want the line at to find the coordinate pair. So essentially does also generate the function for the tangent line. You could also argue that too, but you would need the original function. But you would also need the original function to find that generator function. Oh, okay, so let us begin. And so the way I'm going to solve this problem to find the function, the derivative, is a way that, of course, like for starting right now, you can use, but eventually, again, like I said earlier, like, oh yeah, this resembles an x to the 5th, okay? If you're not able to think like that, you just got to do more practice. So for now, this will always work. Just think about what f of x is and what g of x is. So if this equals to f of g of x, what is f of x? Okay, let's think of the outside function, right? The outside function is just something to the 5th. Let's call that x to the 5th. So remember, f of x is the outside function. F of x is x to the 5th, okay? And then g of x, which is this inside function right here. Okay, that's just x plus 3. And we can always check this by doing f of g of x, right? F of g of x is the same as f of x plus 3. Plug in x plus 3 into this, you get x plus 3 to the 5th, which is this. So you can always check, guess and check if you are really stuck. But then eventually you don't even have to write all this out. You will just know how to apply the rule. So now, remember that in order to find this, we have the derivative. We just have to do f prime of g of x times g prime of x, okay? So this notation may confuse a little bit, but again, it's okay. First of all, let's go step by step. What is f prime of x? F prime of x, okay? And again, what I'm about to do is use a shortcut rule, but I'm not going to tell you how I'm doing it, because we're going to get to that shortcut rule later. But for now, in order to find f prime of x, we got to do the limit definition of this, okay? We got to do the limit definition of this. So this is, if we do limit definition here, that's going to be 5x to the 4th. Just assume I did it in advance for now. Okay? And again, I just want to emphasize, why does this technique matter? Okay? That's something I should have addressed to begin with. If we want to do limit definition on this guy right here, limit as delta x approaches 0, this would be what? X plus delta x plus 3 to the 5th minus x plus 3 to the 5th all over x, all over delta x. Look at this thing. This monstrosity. This will, especially foiling out this guy, will get a little confusing. Maybe put some parentheses here, but this would, oh my god, I faint, man. I'm already on the verge of fainting from teaching you guys all this, but I'm so passionate about teaching, I will do it anyway. But yeah, this is the reason why this technique is so useful, okay? And again, you will even see more of its usefulness as we go along in this video, this marathon. Okay, so f prime of x is 5x to the 4th. So we do f prime of g of x. That's just going to be f prime of x plus 3. And remember, f prime of x is 5x to the 4th, so that's just going to be 5 times x plus 3 to the 4th. Okay? And so now, then we just need to find g prime of x. So what is g prime of x? Okay, now I'm going to tell you right now, okay, this is something you don't need a shortcut rule for, but this should be intuitive. You can use the limit definition here, but you actually don't even need to if you just know what this graph looks like. Let's look at x plus 3, okay? It's a linear function, okay? It has a y-intercept, right? 1, 2, 3, it has that y-intercept. But what do you notice? What do you notice about this function? Look at the tangent lines. What do you notice? What do you notice about their slopes? The slopes are the exact same as the slope of the function. The slope of this function is 1, right? This is in y equals mx plus b form, where m is the slope and m is 1. So the slopes of all these tangent lines are going to be 1. So for any point on x plus 3, the slopes of the tangent lines are going to be 1 because it's the same as the slope of the line itself. So g prime of x is just going to be 1, and you can justify this too through your limit definition, but you don't need to. You don't need to. You just know, hey, it's the slope of the line itself will be the slopes of all the tangent lines. And so now we have f prime of g of x. We have g prime of x. You just need to multiply them now. So this will just be 5 times x plus 3 to the 4th times 1, which will just be 5 times x plus 3 to the 4th. That is the derivative of this. The derivative of this is this. All right, hopefully this example problem is kind of showing you the usefulness, but we will see more of why this is useful as we go. All right, now let's get moving forward into this new world, which is very interesting, especially for a first-time learner. And still, I find it fascinating as I'm teaching this for like the 100th time. This is just awesome stuff. All right, so now we are going to. This is where I said I am going completely off of the traditional sequence of how a traditional Calc 1 teacher would teach this, and that is that I am now going all the way to the realm of exponential functions with the derivative of e to the x, which teachers often wait until students have mastered these regular polynomial derivatives. But the reason why we need this derivative is then to find another derivative, which is e to the x's inverse cousin, the natural log function, which can then help us alongside the chain rule to find these other general analytic techniques, okay? So, let's get started here. Okay, we know that there is a limit, okay, E itself is defined. E itself is like 2.718, E approximately equals that, but E itself equals to a limit, okay? E is defined by a limit, and that is the limit as n approaches infinity of 1 plus 1 over n. 1 plus 1 over n to the n. Okay? This is true. You put this into Desmos. You put this function into Desmos. Or like 1 plus 1 over x to the x. Put this into Desmos. And you see as it goes to infinity, it will have that horizontal asymptote at y equals 2.718. It's very cool stuff. Okay, so this function equals e, or this limit equals e. Okay, and so now the one thing to kind of note about this is that this numerator right here, it is related to the exponent of e. So if we do like e, the limit as n approaches infinity of 1 plus 2 over n to the n, this will equal to e squared, etc. So now I'm just going to generalize this as e to the x equals to this limit 1 plus x over n. Okay, I recommend putting this into Desmos. I can, in fact, let's pull it up here. I actually want to put this into Desmos for you guys. I'm that dedicated. I want you guys to calculator. Let's see if we can put Desmos on here. I would love to show you guys Desmos. Okay. window capture. Let's do window capture. Desmos graphing calculator. Okay. Let me put this here. This is our Desmos right now. Let me put it right here in the corner. Just so I can show you guys, I'm not making this stuff up. So if we put, again, I'm going to rewrite E right here. 1 over n to the n. So let's see, can I do f of n to make it more intuitive? F of n equals 1 plus 1 over n to the n. Okay, so this is the function that defines z. And so if you go to positive infinity, if you actually go all the way to positive infinity, so we're going to go all the way to positive infinity here, you'll see that we eventually get to that 2.718. We got to go really, really far. We got to go really deep to kind of get somewhere close to that. But see here, 2.718, right? We get to that 2.718 right here, right? You see, we get really, if we go really, really into it, as n goes all the way to infinity, look, we're at like 7,100 here, 2.718. So I'm not making this stuff up. This is the function that gives us e. This f of n here, which we're taking the limit of as n approaches infinity, right? Because that's n behavior. We're going all the way, and we see this horizontal asymptote here, which is at like y equals 2.718. So it's really cool. It's really cool stuff. And again, as you go more and more, you'll see like it'll, get more closer and closer to this e as it goes all the way to positive infinity. So really cool stuff. I'm gonna end the screen capture now, or you want? I'll keep it. I don't know. I'll put it off the screen here. We need to use it, but yeah, this e to the x now is equal to this. Okay, and so now if we want to actually get into the realm of this, if we want to actually now find, if we let, again, I'm gonna assume you know this. Maybe take a screenshot of this, pause the video, or look it up, because I'm going to refer to this, okay? If we let f of x equal to e to the x, we let f of x equal e to the x, then f prime of x is going to be the limit. Again, we're using limit definition here. Limit as delta x approaches 0. Limit as delta x approaches 0. And then f of x plus delta x is just going to be e to the x plus delta x. Minus f of x, which is just going to be e to the x. And then all over delta x. Very cool. All right, this should make sense. And so now I'm going to rewrite this, again, using properties of exponents, as the limit as delta x approaches 0 of e to the x times e to the delta x minus e to the x all over delta x. And so now we're going to actually factor out this e to the x, limit as delta x approaches 0, I hope you guys can still see this here, of e to the x times e to the delta x minus 1 all over delta x. Okay, and so now we'll just then move all the way back over here. We will then get e to the x. We can take it out of this limit because this has no affiliation to delta x at all. So we can do that times limit as delta x approaches 0 of e to the delta x minus 1 over delta x. Okay? So, should all make sense. And so now, this should be minus 1 right here, sorry. And so now, our task is to, essentially, I'm going to call this right here, this is going to be called L, okay? So L, you can say this here, okay, I'm going to just rewrite this here, limit as delta x approaches 0 of e to the x, e to the delta x minus 1 over delta x, this equals, I'm going to do this right here, this is going to equal some L here, some variable L. Now, okay, just for those who know their limits a little better than others, hopefully you know that this is a special limit, okay? I'm not going to spoil what it equals to. So let's do this let again, let n equal to kind of thing again. So we're going to let n, bring back this light kind of over here. We're going to try to see here, can I? Is this good? Yeah, that's good. Let n equal to, we're going to let n equal to e to the delta x minus 1, okay? And so now, we can move this to the other side here. We'll get e to the delta x equals to n plus 1, okay? And so now, if we want to solve for delta x, we can just do the natural log of both sides. So if we do the natural log of both sides, we'll get delta x equals to the natural log of n plus 1. Okay, all what I'm doing is correct. I'm just assigning this thing here to n, okay? Moving this 1 to the other side, so we get delta x equals n plus 1. And then to find this actual exponent here, this delta x, just do log, and take the inverse, right? ln of both sides, so delta x equals ln of n plus 1. And so now, if we think as delta x approaches 0, okay, as delta x approaches 0, e to the delta x, right? And again, we're going to use that same logic as before. We plug in 0 here. This will become e to the 0, which is 1. So then e to the delta x approaches 1. And so now then, if this equals 1, e to the delta x equals 1, right? Let's think of this as equals for a second. I know it's approaches technically, but it's better if we see it as equals for now. Delta x approaches 0. If delta x equals 0, right? For example, delta x equals 0. We get e to the 0, which is 1. And so if this is 1 equals n plus 1, these 1's will cancel, and then n equals 0. So then n will also approach 0. Right? Again, it's just these connections as delta x approaches 0. So if delta x equals 0, this will become e to the 0, which is 1. And then if this is 1 equals n plus 1, these 1's will cancel, and then n equals 0. So n is approaching 0, right? So as delta x approaches 0, e to the delta x approaches 0, and then because of that, subsequently, n approaches 0. And so now, L equals to, right, this limit as delta x approaches 0 of e to the delta x minus 1 all over delta x, which then if we do our substitutions here, we'll get the limit as n approaches 0, because as delta x approaches 0, again, n approaches 0. So as n approaches 0, this numerator here is e to the delta x, this e to the delta x minus 1 right here is the same as n. And then that will be over the natural log of n plus 1, which is delta x. Delta x, this delta x right here, is the natural log of n plus 1. Okay, so how do we go from here? Let's do more analytic work. I know you love to hear me say that. We're going to let ln of n plus 1, right? We know that ln of n plus 1 can also be expressed as ln of n plus 1 to the, make this comma small here, to the 1 over n, to the 1 over n, and then to the n power. Okay, hopefully you can see that. This is the same as, ln of n plus 1 is the same as ln of n plus 1 to the 1 over n times n. This is true. Hopefully you understand, because these n's will cancel and then we'll just get back to this. And so now, oh my god, as n approaches 0, okay, as n approaches 0, right? As n approaches 0 here, right? Let's see here, as n approaches 0, if we do like ln, right? We do the limit of this, essentially, is what we do. The limit as n approaches 0. Again, because of delta x approaching 0, n approaches 0, we have n approaches 0 here, so now we have to deal with this guy right here. We're just rewriting this, right? N approaches 0, right? We can write this in here as well, right? Because this limit is equal to the limit of the numerator over the limit of the denominator of this guy. Just looking at the denominator right now, this is limit as n approaches 0, and we can write this inside limit as n approaches 0, ln of, and then this will be of n plus 1 to the 1 over n. And then, hopefully you see this here. Wait, what's going on? What's going on? Let's look at Desmos again. I want to look at Desmos again, if we can pull that up here. If we pull up this other function here into Desmos, maybe this will help us understand what's kind of going on here. If we have f of n equal n plus 1 to the 1 over n, what's going on here? Let's go closer to 0, right? Because that's where our limit is. Come on. Whoops. All right, what's happening? What's happening at 0? What's happening here? What's happening? Look at this. What? What is this, guys? This is E. This is E when it's 0. Look at this. As n approaches 0 of this, we're getting E. And it's undefined here, but from the left hand and the right hand side, 2.718. We're getting E. Isn't that incredible? This is another limit that yields E. This is another limit that yields E. And so when we look at this, this is just going to be ln of E. ln of E. ln of E is just 1. So this entire thing is just 1. This L is 1. That's it. Just 1. Okay. That's all. Okay, so hopefully this makes sense that this then, if we look at this e to the x and the fact that this equals 1, the derivative f prime of x is just e to the x. What? The slope function, the function that generates the slope of tangent line at any point at any x value is itself the same function. That's very natural because of the growth. The slope will grow with the function. It's so cool. All right. Okay, hopefully this all makes sense. I know it's a lot to process. But just look at my work. It's a lot, but hopefully, again, e to the x, its slope function is itself e to the x. That's really cool. That's awesome. All right, now we are going to now go to e to the x's inverse cousin, natural log of x, and find the derivative of that. I know we're derailing, but trust me, it'll all add up to the end. So let's go ahead and do that. And what you're going to see here is that I'm actually going to introduce you to some newer notation that is also used just as much, in my opinion. I'm trying to be neutral here. Not say that prime notation uses more than this one, but they're both used quite a bit in the world of calculus. Of course, there are some other notations that I'm not really going to talk about today because they're not used as often, like Newton's notation, Euler's notation. Hopefully those names sound very familiar. Look up here, by the way. Euler's identity comes from Euler's formula. Very cool stuff. I also got to give a shout out to Ramanujan, all these people. Excellent stuff. First 1,000 prime numbers. Got a lot of stuff above my wall, but whiteboard is the main focus for today. All right. Now, let me introduce you to some new kind of notation that should, again, be a little weird at first, but makes sense. Let's look at f prime of x. F prime of x, the derivative, slope function, gives us the slope. It's the slope function. This is the same as the derivative d with respect to x dx of f of x. Now you may at first be confused. Is this d a variable? Why can't I just cancel these? 1 over x? This is just f of x over x? No. These are not variables. D dx is an operation. It's an operator. This is saying you're taking the derivative with respect to x of f of x dx. Or of f of x. Not dx. That's integrals. Let's not get into that. Okay? This is, you're taking the derivative, and this tells us a little bit more about the derivative. We're taking it with respect to the variable x, meaning we're going to manipulate and do the analytic techniques with respect to only the variable x. Okay, and this is really used when we're dealing with functions like y equals f, like f of x, where we have an x comma y. Now, let me tell you something, right? If we do the derivative with respect to x of, let's just say, x squared, right? Use your limit definition. We used it earlier in this video, and you saw that, hey, this equals to 2x, right? Do the limit definition again if you're confused. This is 2x. Gotta get the light here. This is 2x, okay? And so this is 2x, and then, wait a minute, we learned the chain rule, right? We learned the chain rule. This itself is technically a composition of functions of x. X, and x squared, right? If we have f of x, f of g of x, right, we can say that f of x equals x squared and g of x equals x, right? Because f of g of x is the same as f of x, which is x squared. So this is technically all of these are composition of functions. Even this outer function itself is a composition of functions with x. It's a composition with x. And so really, if we're doing the chain rule properly here, 2x and then times the derivative of this inner function, which is then, in this case, g prime of x, which is 1, because again, you can use limit definition to know that the slope is 1. But in this notation here, because it's derivative with respect to x, it's going to be the derivative with respect to x of x. Right? And ironically, these dx's cancel. Dx over dx is 1. Sorry about this light, guys. It's very dark in my room, and so, but this is like a bar light, so it sometimes blocks. So anyway, dx, the derivative with respect to x is x, right? We have to. We're essentially ignoring this right here, because we know that we'll ultimately get a dx at the end of the chain rule process, right? So that's why we don't even think of this as a composition of functions, but it technically is, and that's because we have this dx always, this derivative with respect to x of x will always equal 1 at the end of the day. But what if we do dx, the derivative with respect to x of something that is not in terms of x? Okay, what if we're doing derivative with respect to x of something that is not in terms of x? And this is where we get into, like, we're not dealing with y as a function of x kind of stuff. And so now I want to ask you, right, let's just say we have the derivative, let's just say we have y squared plus 3. And I do the derivative with respect to x of y squared plus 3. How do I do this? Well, we of course just doing our old-fashioned, again, limit definition type of stuff here, pretending this is like an x kind of function. Like in terms of x, here we'll get a y squared. But then, remember, this is not going to be dx over dx, or derivative with respect to of x with respect to x. This is going to be that times dx of y, and then this won't cancel. So we can't just ignore it, because this will always be there. This will be there. And then that will be plus 3, and then times the derivative of 3 with respect to x, right? And the derivative of a constant, again, hopefully you realize this, again, y, the function y equals 3, right, is a horizontal line, and the slope at every single point is 0. So this will just be 0, right? So this won't even matter, right? And so now, this hopefully, again, this notation is new. I don't expect you to fully understand it, but hopefully, again, use this video as a resource if you're ever confused, once you're fully in the zone and you fully are like into calculus and you're like, hey, I forgot like dy dx, like what even is this? And again, this is an example of something called implicit differentiation. So what we were doing before with the limit definition of the derivative, again, this is something that Calc 1 teachers teach you very far in advance, way after like a month into derivatives or something like that. But I'm teaching it to you right now on day 1 because it'll help us better understand these analytic techniques if we derive them through chain rule and all that stuff. We're going from limit definition to chain rule, which gets us to e to the x, which then, of course, chain rule also gets us to this conclusion, so stuff like that. So I'm all doing this because I'm trying to get it into this very kind of understandable chronological order. I'm still working on this sequencing, but this is what I believe is the best sequencing. And so, again, what this is called the implicit differentiation. What we were doing before was called explicit differentiation. X, right? Explicit. Because we only were dealing with things in terms of x. But what if we were not dealing with things in terms of x? So now we have a y squared plus 3. We have a y here, which is not in terms of an x. And so we're doing with respect to x. And this is why this notation is used so much. It helps us better And again, if I could explain, if I could illustrate this as well with the prime notation, I would, but I actually can't, because this itself tells us more about the type of differentiation, the type of derivative we're doing. Is it with respect to x, or respect to y, respect to z, respect to w, whatever it is. So like again, with f prime here, we assume that it's explicit, so with x only. So f prime of x, I know that this is just d dx, right? Like d dx of f of x, right? That's what I know. Again, don't write d dx alone. You can also, again, like a shorthand, like df of x dx, or again, like you see here, d dx of y. We typically write it as y squared times dy dx. We typically write it like dy dx. But again, if you want to write it fully like this, you can too. I'd recommend it just for starting off, as this notation may be a bit confusing at first, but it hopefully makes sense now. Anyway, so hopefully you understand concept, but like why I'm showing you this notation. Again, these are not variables, it's an operation, it's an operator, and so why? Because of this, we can do derivatives like this and show that this is, while taking a, like you probably think, hey, this is impossible, this is undefined. No, it is defined. You just, first of all, do, oh, by the way, this is, sorry, whoops, this should be 2y. I'm so sorry, I forgot to change that. This is 2y, okay? I forgot that this is the chain rule. Sorry, I completely missed my point here. Yeah, this is the chain rule. Okay, sorry, I forgot to change that. Again, you do the chain rule, right? The outer function, which is that y squared. So you do, again, you have your y here. I like to say y squared, right? This outer function is x squared, so you do 2 times our y. And then derivative of this is dx of y, which is just dy dx. Sorry for not to show that. Sorry for I miswrote, but yeah, this is what I mean by that. And so this hopefully should make sense. Again, I'll probably go more into notation in another video, but for now, this is really as quick as an introduction I can do, while ensuring there's some understanding behind this, because it's really important that you understand the concept of implicit differentiation, at least for what I'm about to do now and this new notation, because now we're actually going to do the derivative of natural log of x. And so now, if we think about, let's use y, right? And we know, let's let y equal to ln of x, because now, again, you can do y prime as well, but y prime assumes you're doing dy dx. So we're just going to use dy dx, ddx, and that kind of stuff in this case. So if we do y equals ln of x here, hopefully you know from logs and exponentials and how they relate to each other that you can rewrite this as e to the y equals x. This is the same exact thing. Okay? E to the y equals x, do natural log of it, says you get y equals ln of x. These are saying the same things. So now we have e to the y equals x, e to the y equals x. We do the derivative with respect to x of both sides. Okay? And so let's first deal with this side. We know the derivative with respect to x of x is 1, and then 1, and then for the sake of composition of functions and stuff like that, like how f of x is x, and then g of x is also x. It's very, very funny. But then this will be dx of x, right, following the chain rule, which will then just be 1. So then this will just be 1 times 1, which is 1. And then that will equal to this thing, which again, we talked about this, right? And I'm going to write this again. Our f of x is, hopefully you see here, e to the something. So we'll say e to the x. And then our g of x is y. So f prime, or again, f prime of x is e to the x, okay? And so f prime of g of x, which is f prime of y, is e to the y, and then times g prime of x, and then g prime of x, which is the same as the derivative with respect to x of g of x, equals to the derivative with respect to x of y. And we just talked about that. That's just dy dx. Right? This is, again, you can just even leave it at that there if you want, but I'm just writing in the shorthand. So this then, f prime of g of x times g prime of x equals to e to the y times dy dx. Okay? So this is the same as e to the y times dy dx. That equals 1. Sorry if the light is kind of blocking here, but hopefully you see here, e to the y times dy dx is 1. And so now, what we're going to do here is I want to solve for dy dx. I want to solve for dy dx, because dy dx here, right, if we let y equal to f of x, okay, y prime is equal to f prime of x, d dx, or dy dx, is the same as d dx of f of x. So this is why dy dx is getting us to the same f prime of x, which is what we want. We want the derivative, which is ultimately that. And so if we do this, we get dy dx equals 1 over e to the y. Okay, now what is y? What is y? Let's go back to the foundations. Y is just ln of x. So this is just dy dx equals 1 over e to the ln of x. What is e to the ln of x? It's just x. These cancel. So then dy dx equals just x. That's all. That's all. So therefore, again, fancy way to say therefore, the derivative with respect to x of ln of x, or we can say if f of x equals ln of x, what is f prime of x? What is the slope function? What is the generator function? This is just 1 over x. That's all. Okay. So, if these analytical deductions did not make sense, I really apologize. Okay, you may have to learn a bit more in class and stuff like that, but this is as best I can do for a pure intro. So if I was a little vague at points, I apologize. And if I went too quick on this, usually teachers spend a few days on this. I spent a few, 10 minutes on this, like on just the notation itself. I apologize again. Watch more YouTube videos if you don't have your teacher at hand. I'm just trying to help you guys understand this to the best of my ability for a pure beginner. So, let's recall. And again, these are easy to remember, so don't act like you have to memorize a lot or like remember a lot. Okay, let's recall what we've learned so far. It's a lot. Okay, it's a lot to take in. Let's just take a little breather, and again, let's kind of synthesize what we've done. So again, it's all related to the slope of the tangent line. This is all for finding that function that gives us the slope of a tangent line at any point on a function, okay? That is really the goal. And so again, f prime of x, and now we can use our new notation as well, right? If we let's let y equal f of x, and so then y prime, which is the same as f prime of x, which is the same as dy dx, which is the same as d dx of f of x. This is the same as the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. This is step 1. And of course, with the new notation, you can see what I kind of did here to show that they're equal. And then also, let's say that we have like f of x equal, I don't know, let's get into e to the x, right? We know that f prime of x, which is the same as d dx of f of x, is just literally the derivative of e to the x. That slope function. That slope function is itself e to the x. And that should make sense, because I guess if you look at e to the x, right, the slope and its exponential growth, you look at the slope itself grows with the natural function. The slope itself grows with it. And so that itself has to be e to the x. It's so cool. It's so cool, and it makes sense. It's intuitive because of exponential growth. Now the slope grows too at the same e to the x. It's really cool. And so now what we've just discovered is if we, for example, let f of x equal to the natural log of x, if f of x equals to the natural log of x, then f prime of x, which is again just d dx of f of x. I really want to expose you to this new notation here, even though you may not understand it fully, which is okay. This is going to just be 1 over x. 1 over x. And so this is kind of what we've learned so far in this most succinct form possible. Of course, we've done a lot of examples, and I've done a lot of commentary. Also, that special limit that yields e, the two special limits here. I'm going to write them down again, just because they're really cool. First one, again, limit as n approaches infinity of 1 plus 1 over n to the n equals e. And of course, how this relates to the exponent, right, e to the first. And then also this other limit here, and we just divide both of these through Desmos too, so you can kind of see why they are what they are, because when you graph them and you see what happens, especially this one, as you go very, very large in the positive x direction, that it eventually equals to this 2.718, which is e. And then here, the limit as n approaches 0 of n plus 1 to the 1 over n, that's also going to be E2. So it's really cool, and you can see this through Desmos. We went through it. Rewind in the video. Try it for yourself. I'm not making this stuff up. This is math. Math is real. Okay? I'm showing you why this works to the best of my ability. Okay? Again, if you have any questions, please let me know in the comments. All right, and so now we're kind of approaching the final leg of this video, and by final I mean this is probably going to take quite a bit too. We're actually going to now derive these analytic techniques that will make us take the help us take the derivatives of like x cubed, x to the 9th, or even 2x plus 5 to the 6th, this composition of function with the chain rules, in seconds, okay, using shortcut rules. And so how we're going to do prove these shortcut rules, because I'm not going to give them to you to memorize out the bat, we're going to actually derive them, is through utilizing concepts such as the chain rule and this new concept of implicit differentiation and the derivative of the natural log of x. These are which we found through e to the x, which we found through the limit definition of the derivative. It's all coming together. I'm intentionally going in this order because it chronologically makes sense for this derivation. And so now we're going to head into the derivations of each of these rules, and then at the end we will go through some maybe some more stuff. I don't know, we'll see how I feel. But anyway, again, I hope you know your log rules. Again, like, I'm not necessarily going to prove those today because it's like more of an algebra thing. We're now in the world of calculus. Hopefully you know your log rules and why they work. I posted a video in Understanding About Memorizing, which is one of my It is my signature series of this channel where I essentially prove formulas. This, again, is like a mega marathon of proving formulas and stuff. And I essentially prove the log rules, but that's sort of an algebra thing, so that's why I'm leaving it out. But hopefully you know, like, ln of AB equals ln of A plus ln of B. ln of A over B equals ln of A minus ln of B. And then ln of A to the R equals to R ln of A. Okay? And so now let's go on to, well, what if I want to take the derivative of ln of x? Okay, so let's let y equal ln of x, or sorry, not ln of x, sorry, what am I saying? I am, again, I told you this at the beginning of the video, I am very sleep deprived. I may make mistakes. I may misspeak. I may miswrite like I did earlier when explaining one of the most crucial concepts that may have confused you even more especially when I wrote the y squared still instead of writing 2y. Really apologize for that again. But anyway, and I just put ln of x even though we just found it. I was just recapping. Anyway, let's say we have y equals to any x to the n. Okay, n can be 1,000, n can be 30,000, and hopefully what you'll get from finding dy dx and how we can generalize this dy dx form, you can find these derivatives, these generator functions, these slope functions in seconds. And so really, in order to first of all do this here, I'm going to space this here, because what we're going to do is we're going to take the natural log of both sides. And so hopefully from your knowledge of log rules, this is going to be natural log of y equals to n natural log of x. And so now I'm going to maybe space this out a little bit, and you'll see y, n natural log of x. And so now I'm just going to do the derivative with respect to x on both sides. I'm going to implicitly differentiate here. Well, explicitly, this will be an explicit differentiation on this side, and here it's going to be implicit because we have a y here. That's something that's not in terms of x. And keep in mind, by the way, n is a constant. N is not a variable. If, again, we're unsure, we'll talk about that after this, after all of our rules, which is just, again, 3 rules. This is the first one. And so now, if we do this, we're going to get, again, we can do the f of x, g of x process. I'm going to let you do that on your own here because I don't want to take up a lot of your time. But this will just be 1 over, again, outer function is 1 over x, right? 1 over, and then g of x, which is y, 1 over y, and then the derivative of g of x times the g prime of x, which is then derivative of y with respect to x, because the prime, remember, is the respect to x. This will be then dy dx. And you'll notice that when we do all of these derivations, it's just always going to be a 1 over y times dy dx on this left side. And then here, one more thing. I want to talk about derivative kind of properties as well, especially with this d dx, this operator. Whenever you have a constant, and this is true with limits as well, hopefully this should make sense, because if you try to do something like this with the limit definition of the derivative, if you are not having an x-related term, just like with the limits, you saw that whenever we didn't have a delta x affiliated or associated term, we just moved it outside of the limit or the derivative. We can do the same thing with constants here with derivatives. This is the same as n times d dx of ln of x. And so if we do this here, if we do this here, we're just going to get, am I doing this right? d dx of ln of x here. Sorry, I was just thinking. This will then be 1 over x times dx dx, or d dx of x, again, because I'm following that whole kind of thought process because we're still new to it. Again, we'll know that obviously we'll eventually get a dx dx, which is 1, so we ignore it. But essentially it's just going to be 1 over x times d dx of derivative with respect to x of x, which is 1, because the slope is 1 of the function y equals x. So now we'll just get 1 over y dy dx equals to n times 1 over x. Now I'm going to multiply both sides by y, and so now we get dy dx equals to n times 1 over x times y. And so now what is y? Again, if we erase these natural logs that we took earlier, hopefully you see that y is just x to the n, right? So we can then rewrite this dy dx as n times 1 over x times x to the n. And then if we look at properties of exponents here, we can rewrite this as n times x to the n over n. This will be, again, same base here, properties of exponents, or this is x, sorry. This is x to the first. This will then just be nx to the n minus 1. So therefore, the derivative with respect to x, or dy dx, the derivative of any x to the n power, right? And this is very useful, especially even if we get into composition of functions and this outer function derivative, which will just be an x to this form x to the n, right, dy dx is just nx to the n minus 1. Nx to the n minus 1. Let's do some examples to kind of show you how crazy this is. Let's do some examples here. Okay, let's take x to the 30,000th power. And I want to take the derivative with respect to x of this guy right here. I want to find that slope function. Limit definition of this. Holy, oh my God, this is impossible to do by hand. This is like, take you like 30,000 years to do this. With limit definition, oh my God, I'm about to lose my voice. Let's see, I have some very little water here. Okay, 30x to 30,000, but we can actually do this in seconds using nx to the n minus 1. This is n, right? This is n. This is n, so this is the same as n 30,000 x times x to the 30,000, which is n minus 1. This is it. This is that function. Right, and if you want to see x squared as well, right, something that we did right at the start of this video, this is our n right here. That's just going to be 2x to the 2 minus 1, which is just 2x. What? Okay. I'm very excited, even though I knew this like years ago. It's really fun. Let's move on to our next rule. This is going to be called this is the power rule, by the way. It's power, I don't know why I'm writing this. Power rule. I just got to put exclamation marks here because this is so cool. This is so cool, especially being, I'd say, my favorite rule. It's because it's the coolest rule to show to your friends who are just starting. Like, hey, this is the derivative of how we did x squared using that crazy limit definition from long back. Now we can do it in seconds. It's mind-blowing. All right, now let's move on to something known as the product rule. So what if we have function, I'm going to show you the usefulness here right now. What if we want to find the derivative of e to the x times ln of x? What? How do we find the derivative of a product? What? How do we do this? Let's use let's use our same strategy. And again, what I did to prove that product rule was through a thing known as logarithmic differentiation. Okay, it's essentially, and again, we're gonna do an example very close to the end of the video where we're unsure what to do. And whenever, again, I'm gonna say this at the end, whenever you're unsure of how to do a derivative outside of the world of trigonometry, just set the thing equal to y. Do the ln of both sides. You get a 1 over y dy dx, and then you pull down the exponent, and it's just, you go from there, and then you eventually get the answer. So if you're ever unsure, just take the ln of both sides and do it that way. That's always my best strategy. And we're going to talk about a situation where you're really unsure. We're going to have to use that. And so, anyway, let us go on to knowing how to solve that derivative like I showed you, that e to the x times ln of x, which is a really weird, interesting function. And I'm going to, let's just for funsies, I know we've had a lot of fun moments here today. Let me show you, well, let's see what that actually looks like. E to the x times ln of x. This is going to, let's see, does this look crazy? Oh, that is weird. That is an interesting function. Wow, that is interesting. Very, very interesting. All right, let us now figure out how to find the derivative of that very interesting function we just saw on the screen here. So let's just say that, we have y. Let's say y equals to some product of functions, f of g of x, or sorry, not f of g, that's composition, f of x times g of x. Okay, how do we do this? I'm unsure. Let's just do ln on both sides. So ln here, probably should have done some spacing. ln, actually, I'll do spacing here. Y equals f of x times g of x. And so we do ln on both sides. And again, same thing here. 1 over y dy. We'll have to do derivative with respect to x on both sides then. So we can ultimately get that dy dx. Okay, and so now, actually, you know what? Let's forget that for a second. Just for a second. I'm going to do this a little, like, I missed a step. Do ln on both sides. And so if we do that then, we have ln of y. This equals to then here, hopefully you see a property of logs, right? I mentioned this, ln of ab equals to ln of a plus ln of b. So this is the same as ln of f of x plus ln of g of x. So now, let's take the derivative with respect to x on both sides. Now we can. And so now, same thing, 1 over y, dy dx, same old thing. And then here, we're going to have 1 over f of x, and hopefully, again, if you're confused, just do that whole composition thing, outer function, ln of x, inner function, f of x, do the outer function derivative of this, then f prime of x. So anyway, 1 over f of x, and then times df of x by dx, which, again, this is f of x is, going to be in terms of x. We can rewrite it as then f prime of x. And then here, this will be same thing, 1 over g of x times g prime of x. And so now what we're going to do is then multiply both sides by y. I'm going to use brackets here, y. And then this will cancel, and then we get dy dx is going to be then 1 over f of x. And I'm going to write f prime of x here. F prime of x over f of x plus g prime of x over g of x times then f of x times g of x. Why? Because we erased the logs that we did here earlier. Y, again, going back to the foundation, y equals to f of x times g of x. So multiply, substituting in the y here for this f of x times g of x. So now, dy dx, it's going to be f prime of x times f of x times g of x over f of x. And then plus, again, just distributive property, g prime of x times f of x times g of x all over g of x. And so now you see here, things will cancel. This f of x cancels here. Canceling again, feels good. Maybe, likely we're going in the right direction here. And so then, now, therefore, dy dx, which is the derivative with respect to x of, and that kind of looks like partial derivative, sorry. Ignore what I just said. I'm just got to make sure it's a straight d here. D dx of f of x, g of x, or f of x times g of x, is the same as then here f prime of x times g of x, and then plus g prime of x times f of x. So to find that crazy product like that e to the x times ln of x, we can just do this, where let's say f of x is e to the x and g of x is ln of x. It doesn't matter. This is how we find the derivative of any product. And so let's do an example again. Let's do that example at the beginning with the e to the x times ln of x for fun. So this will work for any product. Okay, so let's let y equal to e to the x times ln of x, right? And we want to find dy dx. So dy dx equals to, and let's first remember f of x, g of x, so let f of x equal to, it doesn't matter what we set f of x and g of x to, and again, you do not have to write this stuff once you get the hang of it. I'm just doing it, breaking it into pieces, just like we did with composition of functions in the chain rule, because we're just starting this. But eventually we will get the hang of just doing it naturally. So f of x is just e to the x, and then g of x I'm going to call ln of x. And so if we do that here, we're going to get then f prime, again, we can recall that rule. It's f prime g of x plus f of x g prime of x plus, sorry, I gotta write it down. F of x g prime of x plus g of x f prime of x. A really easy way to remember this is just like, they're always like switching, kind of like f of x g prime of x plus g of x f prime of x. Again, you can always do log differentiation like what I just did to prove this generalized formula. You can do log differentiation for any of these. You don't have to use these formulas, but it's just the standard practice. So, and it is kind of faster. Again, once you do like a lot of these problems, we'll say like, hey, this derivative of that plus that derivative of this, and it kind of makes sense. So, we'll have then f of x times g prime of x plus g of x times f prime of x. So this is then f dy dx. F of x is e to the x. G prime of x. G of x is ln of x. G prime of x is 1 over x. And plus g of x, which is ln of x. And then f prime of x, which is then also just same thing, same as e to the x. E to the x. And so this is it. Again, we can do some simplification if we want, but you don't have to. E to the x over x plus e to the x ln of x. And so just for funsies, let's kind of just put this into Desmos again. Just, I'm curious to see what this looks like on the graph, the slope function, the generator function, as I like to call it. What is it? E to the x over x plus e to the x ln of x. And so if we do this, wow, look at this guy right here. Look at this guy. Incredible. Incredible. That's awesome. I mean, it looks so simplistic for something that in essence looks very complicated. Anyway, I am sorry if my voice oh my god, it's like I've almost lost my voice. I mean, I've never talked this long. Well, no, I probably have. But anyway, this is it. It's actually simpler than you think it is. You think, oh, this is crazy. How am I going to find that generator, that mtan function, that derivative? But it's really just this rule. And so finally, to conclude these 3 main rules, and again also all the other rules, the chain rule and all that stuff, which is still important, we are going to do the quotient rule. And after this, I am going to show you a scenario where we do not really know what to do, and then maybe, just maybe, again, you'll obviously know whether I do this or not if you skip ahead in the video. if I cover maybe the trig derivatives. Maybe. Okay. So, what if we had a function like this? Like, let's say x cubed over e to the x, or something like that. How do we find the derivative of this? So, one way, which I think you could do, you could always resort to this if you want, is just treat it like a product times 1 over e to the x. Then use that product rule that we just derived. And again, always log differentiation works too. But there is a formal rule for this where you don't have to then, of course, treat it like e to the x to the negative first power and stuff like that. Again, you can do that, but people typically use the quotient rule itself. But again, do what you want to do. But again, it's all about just speed and the common and standard practice of what students learn in calculus. So anyway, let's say that we have a y equal to f of x over g of x, and we just slap a natural log on both sides. So if we do that, then hopefully you know properties of logs. ln of a over b is the same as ln of a minus ln of b. So this will just be ln of y equals to ln of a, which is f of x, minus ln of b, which is g of x. Again, I know I mentioned this, understanding not memorizing full series, YouTube playlist. I go over why these log properties are what they are. Again, hint, they come from laws of exponents, properties of exponents. So now, we are going to do derivative with respect to x on both sides. Again, same old process, and this is why I'm telling you, if you're really unsure about taking a derivative which is not in the world of trigonometry, log differentiation will work, okay? And again, if I cover trig derivatives, then you'll see why this will not really work for those. Using the stuff that we learned in log differentiation, which is really the epitome of this entire video. So again, same old thing, 1 over y, dy dx is the same as, and this one's kind of a longer one. This is 1 over f of x times f prime of x, same process, minus 1 over g of x times g prime of x. I'm going to multiply both sides by y. And then remember, at the core, and then again we get dy dx. At the core, y is literally just f of x over g of x. So this is just, again, I'm going to put this here, numerator, f prime of x over f of x, and then minus g prime of x over g of x, times then our y, which our y is f of x over g of x. And then now what we do is just distribute. So we have f prime of x over f of x times f of x over g of x minus g prime of x over g of x times f of x over g of x. And then now this f of x will cancel here. And now we just have to do some common denominator work. So again, this will be f prime of g of x over g of x minus g prime of x times f of x over g of x squared. And so now, common denominator here of g of x squared, I'm going to multiply numerator denominator of this guy right here, this term with g of x, and so then we'll have that common denominator of g of x squared. So then we'll get f prime of g of x, or f prime of x times g of x minus g prime of x times f of x over g of x squared. And so this is really it. Again, this cut off here, but I'm going to write it again. We can say, therefore, dy dx, or you can write the derivative with respect to x of f of x over g of x is, again, we just wrote it here. I'll write it again. Here it's cut off. F prime of f prime of f prime of x times g of x minus g prime of x times f of x over g of x squared. And I just want to hint, or I'm going to rewrite this in a form that a lot of other, like how, in a way that, at least when you actually do it more and more, people usually tend to write it as, they write it as, and this is a good way to kind of remember it. People usually do this. It's like, we write as g of x times f prime of x minus f of x times g prime of x over g of x squared. I literally just switch these. I just did that. That's all I did. And the reason why is because, whenever you do these, it's like we say bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared, and that's how we do the quotient rule. And either of these is fine, but that's the quotient rule. Let's just do a quick example here. And I'm going to do it also with the product rule as well, just to show that that is a fine solution too. And then I'll give another sample problem that may confuse you at first. And by the way, FY, one other thing to note, we went over the derivative of ln of x and e to the x. With those derivatives, you can also find the derivative of any exponential function like 2 to the x. You can find the derivative of that. You can also find the derivative of like log of x or log base 2 of x, stuff like that. But again, if you're always in doubt, just use log differentiation. Specifically with this though, use change of base formula. Okay, hopefully you know that from algebra class. Change of base formula here. You can just do log differentiation if you're confused. Alright, so let us do one quotient rule example here. I think at the beginning we did like x cubed over e to the x. So we have, let's say, y equals x cubed over e to the x. And so if we do this here, again, let's let f of x equal to e to the x, and g of x f of x equals x cubed, and e to the x equals to, g of x equals e to the x. Sorry, I'm exhausted. And so now, using the quotient rule, again, I'm going to use that bottom derivative of top minus top times derivative of bottom over bottom squared, because that's how I remember it, but that essentially just comes from that formula, and that quotient rule again, same kind of thing. So, dy dx is just the same, is just bottom e to the x times derivative of the top, 3x squared, power rule, very cool, minus top x cubed times derivative of the bottom. Look at that, e to the x derivative of e to the x is the same thing. Slope grows with the function, and then all over bottom squared, and this is it. This is the derivative. And then of course, if you want to do product rule 2 and rewrite y as x cubed times e to the x to the negative 1, you can too. Because if we do this, we'll get then x cubed times, then here, this is a composition function, a chain rule, right? We put negative 1 in front here, e to the x to the negative 1 minus 1 times the derivative of the inside, which is e to the x, and then plus e to the x to the negative 1, that times 3x squared. Look at that power rule, really cool. That was also power rule right here, but with chain rule, and again, everything is just chain rule because we then have, right, like I said, technically a dx, dx of x, but that always comes with explicit differentiation, and so that'll always be 1, so we never really write that. And so, yeah, now let's do an example of a function where using what we know, okay, and I want you to actually pause the video and try this. This may confuse you. I want you to see using the stuff you know, like the power, product, quotient rule, limit definition, chain rule, all this stuff, if you can do this problem. Let's say we have y equals x to the x. dy dx is what? And just for funsies, let us look here at what this looks like. Okay, interesting. I want to give you a fun fact about this, which you can actually justify through calculus, right? Let's go back to the beginning. Remember, horizontal tangent. Horizontal tangent gives us that relative extrema. If you actually look right here at this number here, there's actually something very special about this number. There's something really interesting about this function. That is that the x value, and you'll find this when that slope function that we find here equals 0, which is where the horizontal tangent line is, right? Horizontal tangent line, right? When the slope is 0, where there's an extrema, you'll actually get 1 over e. How does a function that has no e involved at all have 1 over e as the x value for its relative minimum? In this case, the minimum. What? That is so cool, isn't it? That's really cool. That is awesome. So now, anyway, let's find the slope function, and then we can also take the zeros of that too. We can do a lot of stuff. Anyway, pause the video first of all. I want you to, I'm gonna keep this question mark here. Pause the video, try to see how we can actually find the slope function, and bonus, maybe try to get that 1 over e. Like I said, maybe set the slope function equals 0 to find where that slope will be 0, where that x value, where that tangent line of the infinitely many in the function has that 0 slope, and that's where the relative min or max may be. Anyway, pause the video. Pause it. Do not wait. Pause. Okay, assume you paused it. If you're stuck, that's fine. Anyway, let's see here. Can we do a power rule? No, because x is not an integer. X is a variable, right? You can't. This is not equal to x to the x times x to the n minus 1. This is not equal to that. Sorry. Product rule, quotient rule, no. Chain rule. What do we do here? Do we need to know trig derivatives for this? No. What did I say before? If you're ever in doubt in the world of, outside of the world of trig, use log differentiation. Just slap a log and see what happens. Let's do ln. We'll slap an ln specifically. It's the easiest to deal with. Okay, we'll then have like a 1 over y, dy dx. You get the whole process. That's the same as here. Well, let's rewrite this as, first of all, we can bring this exponent down. This works, properties of logs. It doesn't even have to be an integer, right? So ln of y equals to x ln of x. And so now, derivative with respect to x on both sides. So 1 over y dy dx equals to d dx of this thing, and this is a product rule scenario. Okay, so if you said product rule, you were partially right. I mean, of course, chain rule, also partially right. This is using all our rules, guys. Except for power dx, I don't know. Anyway, they're all being used if you really micro-analyze all of this stuff. So anyway, product rule here, so this is times 1 over x plus ln of x times 1, and then multiply both sides by y to get that dy dx, and so we get dy dx as, and then this will cancel, this will be 1 plus ln of x, and then times our y, which again, going back to the foundations here, is ln of, is x to the x, right? So this is times x to the x. This is our slope function. So let's see here what our slope function looks like, and we can find the zeros of that, right? Our slope function is 1 plus ln of x times x to the x. And if you look at the zeros here, or the 0, this is where that equals 0, which means this is where the tangent line, the horizontal tangent of this is when x equals 1 over e. Right? 1 over e is the same as this, which is really cool. Oh wait, sorry, I forgot to show you this. This is what it looks like. Sorry, this is the Desmos right here. This is the original, right? Same x values, I'm not lying. Same x values. Where is this, right? 0. When this is, again, this is the 0 of the slope function, which means that's when the slope is horizontal, right? Tangent line, well, the slope is 0, which means horizontal tangent right here. It's all connecting. So again, whenever in doubt, just use the log differentiation. Now, I think, you know what, I'm almost dead here. I'm still gonna give you guys one more. Alright, I think we'll save it for next time. Trig derivatives. I think we'll save it for next time, okay? It's already a lot. We'll save it for next time, okay? Thank you guys so much for watching.